neutrinos, there is one correction from last lecture. I told you that the branch ratio for pion 2 electrons was like 10 to the minus 2. It's actually 10 to the minus 4. Mateus got that. The reason is because there is a suppression with respect to the muon branch ratio of like mass of the electron for mass of the muon square. That is of order 10 to the minus 4. There is a few other factors there also, but so yeah, it's not 10 to the minus 2, it's 10 to the minus 4. All right, so we were discussing beam neutrinos. So remember, we said that solar neutrinos were sensitive to this, and to matter effects. We're discussing beam neutrinos, where you measure this, you measure this, and you can measure delta CP. And there is one thing that, I'm not going to go in like gore detail, but there is one thing that you must know if you ever want to understand neutrino oscillation physics results, which is what we call a biprobability plot. It's very common and can be very confusing, so let me tell you what this is. So when you're talking about beam neutrinos, you can plot the probability of nu mu oscillating to nu e versus the probability of nu mu bar going to nu e bar. Of course, the probability depends on energy, so you need to pick an energy, and you typically pick the peak of the energy of some experiment. For example, in NOVA, you would take 2 GeV, which is the peak of the NOVA spectrum, roughly, and you set some distance, for example, 810 kilometers. That's the NOVA baseline. So what happens here is the following. You take one set of oscillation parameters, and that gives you, let's say, with delta CP equals 0, and that gives you a point here. So for some value of theta 1, 2, theta 1, 3, theta 2, 3, etc., this distance, this energy, the nu mu to nu e probability is this, nu mu to nu e bar is that. Fine. And then what you do is that you vary delta CP, and as you vary delta CP, this thing goes around as an ellipse. This should be an ellipse. Let's say this is for normal ordering, all right? If you change the ordering, let me put here a few values. So this would be delta CP equals 0, delta CP equals pi, delta CP equals 3 pi over 2. So in some sense, as you increase delta CP, this guy goes counterclockwise. Now, if you change the mass ordering, because of how matter effects work, remember the matter effects were a combination of delta m squared versus the potential. If you flip the sign of the delta m squared, matter effects affect you differently. If you change to the inverted ordering, you get something like this, where this is 0, pi, pi over 2. This is 3 pi over 2, just as that. Okay? The size of the ellipse has to do with the amount of CP violation. And CP violation can only happen when you have the 3 neutrinos oscillating. Or if you go into the oscillation probability formula with a little bit more care, there is a part of the oscillation probability formula which goes like this. C13, S13, C12, S12, C23, S23. These sines and cosines. Sine of delta CP. And then there is a term here which I'll explain in a second. Oh man, this is big. This business here, like this is a chunk of the oscillation probability. It's not the entire oscillation probability. And I can only write this in vacuum. I can't solve matter effects and 3 neutrinos and all that. It's too complicated. This whole business here without the 8 That's the Yarskog invariant. Oh God, Yarskog. So for those of you who don't know, Cecilia Yarskog derived an invariant quantity, parameterization independent, that gives you the amount of CP violation in fermion mixing. She derived that for quarks, but you can have a similar one for leptons. So if you... the ordering is basically, we know that delta m squared, this guy here, we know this is positive, right? Positive. But we still don't know if this is positive or negative. So the normal ordering corresponds to a mass spectrum where nu3 is heavier than the other two. The inverted ordering is the opposite. So this is inverted ordering, this is normal ordering. And here, just one more thing. This guy's here, delta ij, is just delta m square ij L over 4e. Okay? So you see here that you need all mass splittings to be non-zero, and you need all mixing angles to be non-zero to get CP violation, which means that any dependence on delta CP depends on all parameters. So kind of the size of this blob here will vary as you change delta m squares or mixing angles, okay? As you increase the sign of θ23, this ellipses go in that direction, because there is a part on the probability that has this. So the leading order nu-mu-nu-e oscillation without, like, the leading order does not include CP violation. It goes like this, and then sine square of delta 3-1. This is the leading order term in the nu-mu-nu-e oscillation formula. And as you see, if I increase sine squared θ23, overall, these probabilities grow. Same happens for θ13, but θ13 is actually super well known, so you can't vary that so much. Matter effects distinguish normal ordering from inverted ordering. So if you increase matter effects, the ellipses get further away. This is very, very helpful to understand what is going on with T2K and NOVA. Usually, experimentalists will not give you their data in terms of probabilities for very obvious reasons. They don't measure probabilities, they measure events. But they simply give you like a by-event plot, which is almost in a one-to-one correlation to that for experiments like NOVA and T2K, for experiments where the beam is very narrow. So, since I'm talking about T2K and NOVA, let me just show you what they have measured in terms of this bi-probability plot. So let me just write this and this with bars here, so I, kind of lazy. And this is NOVA. Their ellipses should be something like this, and they see data like over there, right in the middle of everything. Consistent with essentially any value of delta CP, consistent with both normal and inverted ordering. For T2K, what they see, because T2K has a shorter baseline and lower energy, they have less matter effects. So their ellipses are more like this, kind of on top of each other a little bit more. And what they see is something like this. They see actually a little bit more neutrino appearance than what the standard model can predict, given what we know about mixing angles, and a little bit less anti-neutrino appearance, which is a bit confusing, but that's okay. It's within error bars. But there's a funny thing that happens here, which is the following. Alone, NOVA prefers normal ordering, and T2K prefers normal ordering. this is, maybe I should do it in a slightly different color, if I can. Oh, look at that. So, almost perfect. So this is inverted ordering. You can clearly see that normal ordering is closer to the data point, and here you're on top of normal ordering. So individually, they prefer normal ordering. But when you combine these two results, T2K prefers 3 pi over 2 for delta CP, but NOVA prefers delta CP equals 0 if the order is normal. So there is a tension there. And the tension is actually such that if you take inverted ordering for both, it's actually a better fit. So this is how this kind of plot can help you understand this stuff. Alone, T2K and NOVA prefer normal ordering with their latest data. When you combine them, because they don't prefer the same value of delta, they actually have a slight preference to inverted. That is to say that the mass ordering is still a big open problem in neutrino physics. We really don't know what the mass ordering is. We need more data to solve that. This tension, yes, this tension increased a bit, yes, with time, yes. It could be new physics, yes. Although this is like a 2.5 sigma tension. It's not like a 5 sigma tension, right? So it's a relatively small tension. You can fit with new physics. But I would say it's not something that you should lose your nights of sleep for that, right? It's interesting. Don't get me wrong. It is interesting. But it's not like we have seen new physics. There is evidence of new physics. It's more like there is some tension. New physics can alleviate that. But the tension is not so big. Any further questions on that before I move on? Oh, go you then. How well do we know the matter for the baseline? Not so badly. It's about 10%. So like I don't know how you measure that, but you get people who are not me to do that. You probably get samples of the ground and like look at the composition of the dirt, and you infer some density. The nice thing about density, at least in this planet, is that it doesn't vary that much. Like water has density 1 gram per centimeter cube, but if you take the core of the planet, which is like iron, it's like 14. So you're not going to find something in the ground like over here between NOVA in the NOVA baseline that has an average density of 5. Like this would be like a very, very dense rock, maybe some metals or stuff. So of course, the shape of the density profile is way more unknown, but it has been shown by people like Stephen Park and Kevin Kelly that for these baselines, as long as you get the overall matter right, the overall density, the average density, you're good to go. Like you could imagine that there is a density profile, this is density, that is this, and you compare that to something like this, which sums up to the same thing, right? The average is still the same. The change on oscillation is very, very small. It's below the sensitivity of the experiment. There was another question. Yeah. So what you measure is you have an experiment where you, oh yeah, sorry. So it's essentially how do you measure this stuff, right? How do you put this error bar in this plot? So how you measure is you have an experiment with a muon beam or an anti-muon, sorry, a nu mu beam or nu mu bar beam, and you measure nuis or nui bars. What you exactly call nui and nui bar is an experimental question, and I think next week will be more clear for you on that. But the deal is that you measure a number of nu-e-like events, and if this number is larger than the standard model prediction, you're going to be like over there. And the error bar is a combination of systematics and statistics, and this error bar is dominated by statistics. It's essentially Poissonian statistics. You have like 20 events, error bar is whatever, plus or minus root of 20-ish. No, not exactly that, but I'm not a statistician, so. Yes. So for example, imagine that you let the matter, the density of matter vary. You could imagine that as this density varies, the standard model prediction can move. You can always translate that into increasing these error bars. And they do that, but the variation is not enough. Of course, if you had new physics, you could have an extra matter effect that will throw these ellipses a little bit larger, such that now you would have a consistent result between those. So in principle, you could do that with new physics, but with standard physics, given what we understand about the experiment and the error bars, there is a little tension there. All right, so oh, that's great. That's a great question. So the orientation is given by the oscillation probability formula. So imagine that I have an oscillation probability, nu mu to nu e, which depends on energy and baseline, and I fixed those, okay? It depends on mixing angles, mass splittings, and delta CP. So if I just fix all these parameters to things that I have measured before, and I put delta at 0, I get a point here. As I vary delta, it just draws the ellipse. Like, the ellipse could have been tilted and stuff. The fact that it looks like that is it has something to do with baselines and mixing angles. But in principle, if the baseline was different, if matter potential was different, if mixing angles were different, the ellipse could have been different, right? Could look a little bit different. This is just like the prediction of the oscillation probability. Yes, yes. So in principle, if I have 0 matter effects, and I pick the mass splittings properly between normal and inverted ordering, I could actually be on top of this thing. It's not that trivial because there is the solar splitting, so that gives you M1 is smaller than M2 already, and that fills matter effects, although it's subleading. But in principle, let's say if I had only 2 neutrinos, oh, that's a great one. If I had only 2 neutrinos, I don't have CP violation. We have discussed that the P mu E is equal to P mu E bar. I would be a point here. There's no delta CP to vary, so that's kind of boring. So in principle, you could be on the equal line. The nice thing about drawing the line here is because you see more clearly the difference between normal and inverted ordering. Yes. Yeah, so they are completely agnostic because the question is if these plots are agnostic between Dirac versus Majorana, and Majorana phases do not play any role in oscillation physics, so any observable role. So if I tell you that neutrinos are Dirac and I draw the ellipses, and I tell that neutrinos are Majorana and I draw the ellipses, they will be identical. So for 3 neutrinos, the only phase that shows up here is the delta CP phase that comes with that sine theta 1,3. Of course, that if you have a neutrino mass model, I think Matheus will talk more about that later, like imagine that neutrino masses come from some mixing with heavier neutrinos. That means that the PM&S matrix is not really unitary. So this could change. In practice, that non-unitary needs to be very small, such that you don't see on these plots. You can see somewhere else, maybe, but there is essentially no impact here, right? Given the experimental constraints we have, just assuming that there's no mixing with any new species is actually pretty good. How does the ellipse change when you change energy and distance? Yes. So let's look at this, for example. This guy here, let me write it explicitly. We have delta m squared 3.1 L over 4E. If I send, let's say, the energy to a very large value, then I don't have oscillations anymore. So if I send the energy to a very large value, this ellipse will start coming closer and closer to 0, right? So there is a limit in which I send the energy to infinity, the probability is 0, we're done, so you're at a point here. If I change the baseline, it's kind of similar to the energy, although so matter effects do not depend identically on energy and baseline. So it's not exactly the same, but it would be similar. The reason why you choose these values that you choose is that you want to see where oscillations are the largest, so that you can like design your experiment, for example, right? If I tell you here is $1 billion, so so if I do that and I tell you, design me a neutrino oscillation experiment to measure something like delta CP, what do? Do you make larger matter effects, longer baseline, lower energy, higher energy? And this kind of plot tells you that if you want to see, for example, the ordering, you rather have more matter effects because they split the ordering. If you want to see delta CP, well, it depends if you know the ordering or not, because there is a degeneracy here. So this helps you out in like designing experiments and understanding the results. All right. Can I keep going? Okay, I'll keep going, but you can always ask questions. So, all right, so I'm done with beam neutrinos. Let me just tell you a little bit of atmospheric neutrinos and reactor neutrinos. And then, if time allows, I'll do actually one calculation. Does time allow? Do I have time? Okay, cool. All right, so atmospheric neutrinos. So the way atmospheric neutrinos are essentially neutrinos created when cosmic rays hit the atmosphere of our planet, right? So this is the Earth. You have your detector here. And then cosmic rays are coming. Like cosmic rays are like protons or whatnot. They'll hit the atmosphere. When they hit the atmosphere, they'll create a shower of particles, like pions and kaons. And you can see like some similarity with the beam. And then these guys will end up decaying eventually into neutrinos, right? There is a lot of similarity, actually, with beam neutrinos in terms of production. You are just hitting stuff on stuff, creating mesons and waiting for them to decay. You don't really wait, they just decay. It's the atmosphere. But the nice thing is that now you have a flux of neutrinos that is fairly isotropic, because the cosmic rays hitting the planet are isotropic. It's not exactly isotropic because the Earth has like magnetic fields and complicated stuff, but it's fairly isotropic. And the interesting thing about this neutrino sample of atmospheric neutrinos is that first, if you understand where the neutrino comes from, like when the neutrino interacts, produces you like muons and stuff, if you can reconstruct the neutrino direction, you could say that the neutrino crossed the core of the planet and the mantle and the crust, for example, and they have different density profiles. If they come from somewhere else, maybe they only crossed the crust, and so on and so forth. So this gives you a very, very rich neutrino phenomenology. Of course, very rich for a theorist, usually translate into very complicated for an experimentalist. Because now you need to reconstruct the neutrino energy and direction, and you don't see neutrinos, and you need to fold that in with how neutrinos oscillate, fold that in with big uncertainties of like, what is the flux of cosmic rays? What are the magnetic fields and how do they affect these cosmic rays and this meson production and so on and so forth. So there are large uncertainties, but this is like a very valuable sample of neutrinos which actually helped us discover that neutrinos do oscillate. So the key here, I'm not going to go into details, but the key here is that you need to have the direction of the neutrino. Somehow you need to be able to reconstruct that. You need to reconstruct the energy of the neutrino as usual. Matter effects are very important, at least from a theoretical perspective. Experimentally, it's not trivial to see these matter effects, but they're there. And the flavor of the neutrino is a little bit different from beams because a muon will decay to a nu mu. A pion will decay to a nu mu and a muon. But usually you have enough distance for this muon to actually decay. So this muon will decay to nu e nu mu. So you have actually a non-trivial component of nu e. In beam neutrinos, the typical nu e contamination is like few percent. Here, it can be 50%. So I have lots of nu e's. Yeah, maybe this is all I want to say about that, because if not, I'll never finish. So this is super interesting, but I'll not go into great detail here, okay? The last thing I want to say about production, actually there is one thing I want to say about this. Cool, that's fine. So you measure the so-called atmospheric parameters with atmospheric neutrinos. And the name is not a coincidence, right? You call atmospheric neutrinos because, atmospheric parameters because you measure with atmospheric neutrinos. And the last thing I want to say about measurements is reactor neutrinos. So reactor neutrinos, you basically have a nuclear reactor like our dear Angra or Atucha in Argentina. And nuclear reactors actually emit a lot of neutrinos. They emit about 10 to the 20 neutrinos per second if they are commercial reactors. Like order 10 to the 20 neutrinos per second for a gigawatt nuclear reactor. These are all nu e bars, and their energies is kind of like, this would be like number of events. It's folded in with cross-section. It peaks about 4 MeV or so. So they're not very high energy, but there is a lot of them. So what you do is that you detect these guys with a very important reaction for neutrino physics, the inverse beta decay. So beta decay and neutron decay to neutrinos and stuff. Inverse beta, the neutrino gets absorbed and generates stuff like this. Nu e bar, proton, e, neutron. So a neutrino, a nu e bar interacts with a proton in your detector. Usually these detectors have like carbon, hydrogen things on them. And they emit a positron and a neutron. And by how you see these particles, you actually have a very, very decent signature for these events. You can cut a lot of backgrounds, super strong, super good, nice cross-section. The only drawback is that you can only see nu e bars. So the only thing you can probe here is the nu e bar disappearance rate. Energy is too low for you to produce muons, so even if the nu e bars became nu mu bars, you can't measure the nu mu bars, right? You just measure that. And this thing gives you theta 1, 3, and delta m square 3, 1. If you do at a shorter baseline, if you do at a longer baseline, like Kamland, you actually measure the solar parameters, okay? Okay, so this is all I wanted to say about oscillation results. Any questions, comments, confusions, complaints? So theta 1, 2, reactors do have sensitivity to that. Kablan is the main experiment that measures that, these two guys. But theta 1, 2 is actually way better measured by solar neutrinos. So essentially, if you look at sine square theta 1, 2, and, oh, sorry, I think sine square theta 1, 2, and delta m square 2, 1, solar neutrinos give you like a blob like this. So it's a good measurement of that. And Kamlan gives you like kind of a blob like that. So it's a good measurement of the mass splitting. So by combining the two things, you actually measure both, right? There's a lot of neutrino physics that you can't do with a single experiment. You need to combine several experiments to be able to extract the oscillation parameters. Oh, that's great. So the flux of neutrinos here do not really depend on where they come from. It's isotropic. But as you look at neutrinos at the horizon, let's say, and you start looking down, just by the production of this stuff, you expect some zenith dependence on how many, let's say, mu neutrinos you have. If these neutrinos oscillate, the zenith dependence will change. And this is what you see. So there's a cosine of the zenith angle. So zenith angle is like cosine equals +1, I think. So neutrinos are coming down at us. -1, they come from the other side of the planet. And these like events. And you have some prediction. And what you see is something like, for example. And then this deficit, you say this is oscillation physics. Of course, experimentally, it's not that simple ever, right? You need to understand your uncertainties, the uncertainties on the predictions, et cetera, But on the other hand, there is a lot of different energies, flavors, and zenith angles to look for. So when you have several predictions for several different, let's say, setups, and they all agree with oscillation, kind of needs to be oscillation. No, I think you have actually less. Yeah, I think this is the pole. No, it's not really the pole. No, sorry. This is from the experiment. So it's the zenith from the experiment. I don't know. I don't know. There is, so it depends on the energy also, because you have a magnetic field. If these cosmic rays are low energy, gives you low energy neutrinos, you expect a big impact of the B field. But if they are high energy, they don't care that much with the B field. So it's not super trivial. It's not super trivial. But people do take that into account. No, so actually, for example, if you take Super Kamiokande, which measured atmospheric neutrinos for like 30 years, they are big tank full of photomultipliers to detect the Cherenkov light emitted by stuff that neutrinos produce. They can see all zenith angles. So you can do things like, I'll look at, this zenith angle, that zenith angle, but in practice, you want to leverage at most, like the best you can your data. So you do look at everything possible. And Kamiokande and Dune in the future, they will both be able to look at all zenith angles. There could be like some zenith angles could be easier or harder because these detectors are not like perfectly spherical and symmetric. But overall, you can look at all that.
Just to make sure I understand correctly, the oscillation deficit is because the neutrinos are from inside the Earth, so you have more oscillation.
Yeah, so mu neutrinos come from inside the Earth. They oscillate into electron neutrinos and tau neutrinos, mostly tau neutrinos. And then you have a deficit of muon neutrino events at the, let's say, GeV, few GeV scale.
From inside the angle.
Yes. If you produce a neutrino here, the baseline is actually very short, right? It's just the atmosphere. If you produce down here, you have like 10,000 kilometers. Yes, yes. So basically, this kind of deficit, if you think about the old days, when we actually didn't even know if neutrinos oscillated or not, this kind of deficit was a big, complicated problem because you could say, well, you don't understand the model of the neutrino flux. You just don't understand cosmic rays well enough. Just like people said that you can't understand the sun well enough to say that there is a third that disappeared. Your prediction is wrong. So these things are complicated to get solved. It usually requires, for example, in this case, 2 different predictions for solar neutrinos and atmospheric neutrinos that are both consistent with oscillations. Because when you have that, then it's like you really think that we got it wrong on the 2 completely different problems with independent systematics, independent predictions. It could be, right? But this is like, it's doing science, right? Like you claim something, half the people will say you're wrong, the other half will say you're right, and the other half will just don't care. So it's always complicated, but yes, this is similar to the solar neutrino problem.
Can you explain when you looking at answer, why is mostly auditory for you?
Oh, that's just how oscillations work. So because θ13 is a large angle, at atmospheric distances, the muon neutrino oscillates a lot to tau neutrinos and just a little bit to electron neutrinos. Essentially, the oscillation of mu neutrinos to tau neutrinos goes like this with a 2 here. And this mixed angle is approximately 45 degrees, so this sine square of 2 theta would be about 1. For nu mu to nu e, there is a sine square 2 θ13, and this thing is like less than 0.1. So it's just how nature chose the parameters. Doesn't need to be like that. Well, it's like, neutrinos can oscillate according to mixed angles. They can oscillate more or less. The mixed angles define how much they oscillate. It happens that mu neutrinos oscillate a lot to tau neutrinos at atmospheric distance. And that's driven by the fact that θ23 is large. Because θ13 is small, you have little nu mu to nu e oscillations.
So then perhaps we struggle with the fact that why are the lapses?
I don't want to go there. That's too confusing. All right. So now, in my last, 20 minutes or so? 15. Let's do a calculation. And I think this will be fun, allegedly. So here's the thing. There are all these ways that I told you how to detect this stuff, like neutrinos interacting with nucleus, inverse beta decay, neutrino electron scattering. But there is a new way, relatively new, of detecting neutrinos. It's actually fairly recent, because like in neutrino physics, 10 years is a short time scale. So it's very, very recent that we have seen this new way of detecting neutrinos, and that is called the coherent neutrino nucleus scattering. Coherent neutrino nucleus scattering. So what is that? By the way, people call this, for short, sevens. You say like the number 7, but several number 7s. And this is never a nu, it's always a V, because we are lazy on LaTeX, okay? So everybody calls it 7, just call it 7, it has been decided already. So what is that? This is a cross-section in which the neutrino comes, and it exchanges not too much energy with a nucleus, and instead of hitting the nucleons in the nucleus, it hits the whole blob. And the reason why that is interesting is because when it hits the whole blob, imagine this, right? Imagine that you throw an electron around, near a charged a charged object, the electron fills the entire dense charge of this object, not every single charge individually. And this is kind of the same. The neutrino fills the entire weak charge of the nucleus. So there is an enhancement on this cross-section. So the way this works, and I'll do this calculation. I don't have time to like do the entire thing in detail, but I'll do a little bit of that for kind of a weird reason. Because when I was a student, and I have always been a theorist, at some point I didn't know how to calculate Feynman diagrams, and I didn't ask, and I started to get ashamed of that, and that only made me like not learning how I do that for more time, which is just stupid. I should have just asked it. So I'll just do this, a little bit so that if you never, if you have confusions here, at least you see once. And if you are ashamed, that's okay. We're all ashamed. We all suck on something, which is fine. We're all ignorant. So you have a neutrino, you have a nucleus, and the Lagrangian that describes this interaction is an effective Lagrangian that goes like this. There is a G over 2CW nu gamma mu P left nu. There is a G over CW. CW is the cosine of the Weinberg angle or the Wick angle. Neutrons, gamma mu, minus 1 over 4, and I'll tell you where these numbers come from in a second. G over CW, protons, and clearly I'm not doing this properly because I'll just do this with a Z, okay? You always need to contract Lorentz indices, right? This comes from like, if you take the, what's the name, Gell-Mann, Nishijima, something. This guy here, the relation between charge, isospin, and hypercharge. There's a lot of different ways of writing that. This is what I just like this way, but you can write with factors of 2 here and there. That tells you how your particles couple to the W and the Z, and you can just use this to calculate these coefficients here, okay? I'm just taking here only the vector couplings because, and by vector couplings, if you don't know what that means, are couplings that goes like gamma mu, fermion. This is a vector coupling. Because the vector coupling will fill the entire charge of the nucleus. I could have taken the axial vector couplings, gamma 5, gamma mu. These would be axial vector couplings. But this thing, you can show that it couples to spin. And if I take a nucleus like silicon, I don't know what. So silicon Z is what, 14? So the number of protons is 14. So the overall weak charge would be about 14. But the spin, I don't know what the spin is. It's definitely not 14, right? It would be like, I don't know, 0 or half or some small number. So usually the axial coupling is not that important. So how do you actually calculate this? Let's just do this, this calculation here, or at least set this up, and then we can wrap it for today. So, and this is going to be like super basic. If you know how to calculate this, you can take a 15-minute nap. We always start against the arrow, okay? This particle. So if it's a particle, it's a U. Let me put 1, 2, 3, 4, so I can write this a little bit more compact. Against the arrow particle, U1 bar, that's the spinor. Now the coupling here, that's this guy. So G over 2 cosine theta weak, gamma mu, PL. Then the other guy, U, I did it wrong, these 3, U1. Remember, a spinor is an element with 4 indices, gamma matrices, 4 by 4. So I have basically 1 times 4, 4 by 4, 4 by 4, 4 by 1. This is a number. This is a number. It's just a number. Now I have a propagator, and this propagator goes like G mu nu, Q mu Q nu, mass of the Z square, where Q is the momentum transfer here, and then Q square minus mass of the Z square. And now I go to the other side, and the other side will be very similar to this. U for, let's take this. So because you are interacting coherently with protons and neutrons, that spinor will be the spinor of the entire nucleus, and the charge will be the sum of these charges, right? So this is gamma mu, let me put the sum of the charges. So it's G over CW, the number of protons times this, 1 over 4 minus SW square, plus the number of neutrons times that, minus 1 over 4, gamma mu U2. U2. Good? Is that okay? Sorry? Oh, CW is the cosine of the weak mixing angle, and SW is the sine of the weak mixing angle. These guys show up in weak interactions, and the MW, the cosine is the MW over MZ, right? We good? All right, so now comes a boring part where you gotta, this is the amplitude. You gotta square this amplitude, and you're going to get a bunch of spinors, and you do an average on spins. And when you do that, there is a bunch of traces. Like that, just show you what happens with this term here. When you square the amplitude and you average on spins, you get stuff like U3. Let me not write this coupling. Let me just focus on the this stuff. And then U1, U3. It's just a dagger. You can calculate that easily. And this can be written as the trace of U3, U3 bar, mu, PL, U1, U1 bar, PL. And then you know that these things here, when you're summing over spins, will become P3 slash M3, P1 slash M1. These are neutrino masses. I really don't care about them. And then you can solve these traces. Traces are a pain. There are rules. If you never solve traces, you gotta solve traces. If you did that more than 5 times in your life, don't do it again, right? Just get fine calc in Mathematica, and boom, be done with it. At least this is what I do. But if you really want to be like, you know, every time I see the traces, I'll solve it myself, like, go for it. It's just a pain. Good, so there's more stuff here, right? Which I didn't write. Like this part and the propagator and so on and so forth. So these expressions will be big. And the best way, in my opinion, to solve this is never to write explicitly what a momentum is. You always solve things in terms of S, which is P1 plus P2, which is also P3 plus P4, T and U, and this guy is P1 minus P3, P1 minus P4, and so on and so forth. Where in my convention, P1 is coming in, P2 is coming into the vertex, but P3 is coming out, P4 is coming out. Some people like to put all the arrows coming in. it can look weird a bit because like, why are all the momenta coming in? But it makes these expressions actually all with plus signs, which is nice. But when you solve that, do not write out what P whatever is. Always try to write in terms of S, T, and U. The amplitude is a Lorentz invariant. It will be an S, T, and U are Lorentz invariants. It will always be possible to write any amplitude in terms of S, T, U, and masses, okay? So do not try to like, oh, in the lab frame, no, not lab frame yet. So this is not little work, this is a lot of calculation, but it's roughly straightforward if you know the rules. And after that, we only have the amplitude. Amplitude, I don't know what's good for. So you gotta have a cross section, right? So what you do is that you open your dear friend PDG, and I mean it, right? PDG has a lot of good stuff. If you're in doubt, go to PDG. You go to equation 49.33 in the kinematic section, where it shows the relation between a cross section and an amplitude. It gives you this. The differential cross section as a function of t, look at that, PDG also uses ST and U, is 1 over 64 pi s 1 over P1 center of mass square vector modulus square amplitude square. Again, amplitudes are Lorentz invariant. Cross sections are area, not Lorentz invariant. This is why you have stuff like this here. If you look and say, oh, but this is why center of mass? Because it's not a Lorentz invariant, right? T is the momentum transfer. You can calculate that, and you see that T is just minus 2 mass of the nucleus, recoil of the nucleus, I think, where the recoil of the nucleus is defined as the energy of the nucleus minus the mass of the nucleus. It's just the kinetic energy, okay? Oh, and there is one thing that I didn't put here on this business, because up to here, it's all good, but implicitly, we are considering protons and neutrons to be elementary particles. And that's not really correct. Or in this case, the nucleus to be an elementary particle. If you increase the momentum transfer on this interaction, you don't see the nucleus anymore, start to see the stuff inside the nucleus. So you always need to parameterize how you lose that coherence when you scatter with a nucleus. And the way you parameterize that is by adding here a form factor. If you're not familiar with that, a form factor is just a function which parameterizes something like your ignorance about something, right? There are tricks about form factors, like you know that form factors respect Lorentz invariance, so there are ways you can write them. It's not just like any function of anything. But in the end, form factors can be like calculated under certain approximations or measured. This form factor, it starts at 1 at low energies, so you see the nucleus as a whole, and as you go to higher energies or higher momentum transfer, these form factors fall to 0. That means that if I shoot a 1 TeV neutrino in a nucleus, the chance that I scatter coherent with the nucleus is very small because I can see the quarks inside it. But if I shoot a 1 MeV neutrino in a nucleus, I mean, what else can you see? You can see the details if you have low energy, so this form factor becomes 1, okay? Finally, 5 minutes? Oh, okay, I'm essentially done. I'll just write one more equation. You plug things in, and now, I mean, cross-sections are experimental quantities, so now you need to tell me if you're in the lab frame, what do you want to measure, and write things properly. And this is a step that you should never skip. When you write stuff, like, there are many ways to do a calculation. They're all correct, but there's only one that is really correct, which is the good one, right? It's like, imagine that you write the whole equation as a function of the outgoing neutrino energy. I mean, you don't measure that. Why would you ever do that? So you write stuff as function of what you see or what you measure, what is observable. If you don't know what that is, if you're a theorist, talk to your experimentalist friend, right? Your experimentalist friend will say, you want me to measure the neutrino energy? I'm sorry, sir. I can't do that. But maybe a nuclear recoil, that may be possible. So in the end, when you do all these calculations, you get this. D sigma, oh, and I changed the notation. I apologize, but, oh, no, this is actually wrong. OK. The ER, so I'll just fix it, is approximately where I'm dropping like very small terms, which, if you think about it, the recoil energy of the nucleus is very small. It's much smaller than the energy of the neutrino usually, or at least smaller than, usually much smaller. The energy of the neutrino is much smaller than the mass of the nucleus. So you can be a little bit careful and drop a few terms which are small. And this cross-section becomes this. And we can stare at the cross-section for like 1 minute, and then I'll finish. Mass of the nucleus, form factor square, function of Q square. Number of protons, 4 sine squared theta weak minus 1. Number of neutrons, which I'll just write as n, square, and then 1 minus mass of the nucleus, recoil, neutrino energy square. Oof, maybe a 2 here. So let's stare at this for a second, and then we can wrap it up. G Fermi square, weak interactions, can't avoid that. This is why neutrino physics is hard. Mass of the nucleus, that's a big number, but don't get misled here because it is a big number, but it also suppresses the phase space. So you don't really gain a lot on the total cross-section because of this mass. Form factor, if you go to high Q, this goes to 0. The interaction is not coherent anymore. This is the weak charge of the nucleus. Exactly how people define the weak charge can vary by factors of 2, because this, it's kind of a dumb definition. But there are 2 important things here. You see that the charge goes like number of stuff squared. If you scatter on protons, you just count the number of protons. Here you square the number of protons. So this makes this cross-section relatively big compared to other neutrino cross-sections. There is also this, which is very interesting. The weak charge of the proton is 4 sine squared theta weak minus 1, whatever. But sine squared theta weak happens to be 0.23-ish. When you multiply that by 4, you're almost at 1. So this term, kind of by chance, is actually kind of close to 0. So protons do not contribute very much to neutrino nucleus coherent scattering. What really contributes is the number of neutrons, OK? And this is just how the cross-section goes. So take-home messages. This is a relatively big cross-section. It requires you to leverage this. It requires you to be able to detect small nuclear recoils. Not every detector can do that. NOVA cannot do that. MINOS cannot do that. T2K cannot do that. But our dear Connie here in Brazil can do that. Or Violeta in Argentina can also do that. So these silicon CCD detectors can actually go to very, very low nuclear recoils. But you got to have a special detector for that. Last thing in my last 30 seconds is, one, you can use this to study neutrino physics. This is great. But again, in neutrino physics, every time there is good news, there can be bad news, although this is not really bad news. This also means that if you're looking for small signals, neutrinos can give you a background with a cross-section that is on the large side with respect to weak cross-sections. What do I mean by that? If you look at dark matter experiments want to measure when the dark matter scatters really softly on the nucleus. Solar neutrinos can also do that for you. Eventually, dark matter experiments will get to what people use it to call the neutrino floor, which is the point where the neutrino background does not allow you to claim the existence of dark matter if you see a signal, if you see something. Today, people call it the neutrino fog, essentially because they're getting close to it. So they don't want to say it's a floor. There are ways that you can like beat the neutrino fog or floor. It's not trivial at all, but there are ways. Well, first we need to get there, and then we beat it. But yeah, I think I can wrap it up.
We have time for one question. No?
All right.
No? So let's thank the speaker again.